Okay, so the plan is to have one more homework in this class. The homework will be out later this week. Then will basically be the final after this homework. Okay. And the final again will be cumulative. We'll cover everything that we have talked about in this class. We're probably not going to change the timing of the final because no matter what day I pick, something else will be happening on that day for somebody else. Okay. So the idea is to say, so the final will be the Thursday, Friday. That's the last week of instructions. Will be released on Thursday. Give you a chance to look at it. Friday at this time of the lecture, you can ask questions. So you can welcome to come here. I'll be here. You can ask questions. The final will not be very long. You should be able to do it within 2-3 hours. It's not take home and ideas take you 8 hours to do it. It'll be 2 or 3 hours for you to do it. You can pick any 2 or 3 hours you want during that time to do it. Any questions about that? So again, right? So the only restriction is must be your own work. Otherwise, you can look at whatever you want for that fun. Okay. So don't copy. Don't copy. It's very easy to tell if you copy from each other. So don't do that. Otherwise, should be not too difficult. Again, try to have a look before Friday. If you send me email, Friday night asking for clarification, I may or may not see that. Right? So try to take a look as soon as it is out to see if all the questions make sense to you, then try to do it. Try to do the question. All right, so ancillary services. So here we can still do some math. So the homework question will cover this. After this, we'll look at planning problems and other economic problems. There'll be less math. The math will be too hard to be in a course context, right? So they'll be increasingly moving towards more difficult optimization problems, not really sort of solved using computers. After this, we'll be looking at problems that'll take a computer sort of fair bit amount of time to solve. Okay, so it's not that there's no more math after this. It's when the math gets too hard in this class. For ancillary service, still there's some things we can numbers we can compute and calculate. Okay. So again, if you recall from last time, the whole idea of having ancillary services is because the power system changes all the time. Right? So the load changes all the time. Other than the load, the generation changes all the time. The transmission topology changes all the time. And there's not, so some of these outages are called planned outages, where this line will require service around this time. But most of these changes are just random stochastic changes. Okay, you don't necessarily know what change has happened. And so the first basic thing of ancillary services is frequency. Right, so it's the frequency change, right? So the basic model is you have something this is a rotating generator or synchronous generator at 60 Hertz. This is supplying a load, right? So changing this load, how it shows up in the frequency of the generator, and the generator measures the frequency change to determine how it should respond. Okay, so every generator basically runs a control loop like this. Okay, so what the generator does is, this is your generator, and you measure at this terminal, this is the frequency of the generator. Okay, so you know how fast this generator is spinning. You can measure this. You take a difference with the nominal frequency in the generator. Okay, so this is the nominal frequency in the generator. So you subtract away the nominal, subtract away this nominal frequency, then this gets feedback. So there's a block. So this is your generator. There's a control block that changes the power output. So this is P power, how much power your generator is actually trying to generate. So basically how this will work is you measure the frequency. If you're a gas generator, there's a valve determining how much gas you put into this generator. So the frequency is too low, you put in more gas. If frequency is too high, you take out some of the gas, okay, in this generator. And then you keep measuring output frequency. And the hope is this two will match, they'll be zero, and you operate at a steady state. Okay? So this is, again, the entire reason why the power system can operate together as an interconnected system. Right? So the nominal frequency, again, this is a number that's hard-coded into everything. And okay, so this is how the system works. And right now, a very hot topic in research is basically what happens if you replace some of the generators with things like solar or wind. Okay, so if you replace this, so before, if you think about the situation as, so the conventional system, you have a few big generators going to a grid. You have load coming out of this grid, right? So this is your conventional generator system, and your control knobs are these big generators. So the load changes, you vary the frequency on these big generators, and then you hope you balance supply and demand of the load. Okay? There's a bunch of control problems you have to think of. Again, these generators should not fight against each other, right? If they're all measuring 60, how do you deal with the fact there will be small measurement errors at all the terminals and so on? But that's sort of in some sense, solved problem. You can deal with this. Okay? And the nice thing here is these are rotating machines. So it is a physical response that if the load changes, they will speed up or slow down. There's nothing you can do there. That's just how they will respond if the electric load changes in the system. So now if you look at the newer system, or I say if you look at the current system, what we have today, so this is still grid, you still have load coming out. We still have a fair bit of big generators around, but we starting to have some smaller things that is maybe sort of power electronic based. Okay, so you have things that are electronic based now, right? So solar, for example, there's no rotating parts in solar. It's purely electronic. In wind, actually, wind is also considered a electronically based resource into the grid. Anybody know what that is? Anybody taking wind energy? So wind, you will imagine there's a blade that's spinning, right? There seems to be a lot of mechanical inertia. But from a grid perspective, nowadays almost all wind is actually we think of as sitting behind a converter. Why is that? Anybody? Okay. Right. Right. So the challenge with wind is, right, so grid is 60 hertz. How fast does wind blades typically spin? Ballpark wise. Is it 60 hertz? Right, it's better not, right? So hopefully not at 60 hertz. Hopefully much slower at 60 hertz. So wind blades, big wind turbine typically spin at something like 30 RPM. Okay, so 120 times slower than 60 hertz. It used to be as we use gearbox to up convert that rotation to 60 hertz. So it used to be you have this bunch of gearboxes converting that. And in those cases, wind is actually a synchronous machine. There is something rotating at 60 hertz. The problem with gearboxes is those are the things that breaks most often. And it's way too complicated to have all those gearboxes. Those are the things break. So now what we do is we take the wind power, it's AC, we convert that to DC. Then you convert that DC to 60 hertz AC. Okay, so then If you look from from the energy storage point of view, you don't see this rotating inertia directly from the grid. So these are inverters, right? We have inverters. Okay. So now the question is, if now these loads start to change, they will respond. What do these things do? Okay, so now it's a question is what do they do, right? So should they respond? If they can't respond, how would they respond? So right now, this is not a very pressing issue for most systems. It's because a lot of systems still dominated by synchronous machines. Like Seattle, we have 90% hydro, so there's 90% of it is synchronous machines. Rest of a little bit, you have electronics. It's okay if they don't do anything, actually. It's okay to just be there. But then if you look at future systems, is basically you have grid. You'll still have some synchronous generation. You'll never get rid of all synchronous generators. One, because hydro is synchronous, right? It doesn't make sense for us to phase out hydro. Right? So hydro is about as cheap as you can possibly get. It's clean, it's cheap, is what you will want to use. The hydro will be there. Nuclear seems to be there for the foreseeable future. We're not growing in nuclear power plants, but it seems whatever we have will be there for the next 30, 40 years at least. So some synchronous generation will still be there, but a lot of the system will be this sort of tiny little inverters that's connected to the system. Okay, so the system, the ancillary service is harder to think of. It's hard to think of what do you do in this kind of system. Is you still have to respond to frequency because you don't want your hydro power plant to blow up on you. Okay, so they have to operate at some frequency. These are 60 hertz. These are hard coded into the machine itself. So you still have to make sure it's okay for them. But now you have a lot more electronics. Okay, so there's two questions here. One is control. How do you control this power electronics to make the system stable? We know quite a bit here now. There's a very active area of research, but there seems to be at least possible to control the grid. The second is economics. This is considerably harder for this type of system. Okay, so right now, if you're a big generator, you don't necessarily get paid to do frequency response. You're basically told you have to do it. Okay, you basically, this is enforced on you. You have to do it. And overall, it actually balances out for you. So what happens is you get paid at a constant hourly rate, right? So this is we're supposed to generate on the hour. You wiggle around this thing, sometimes more, sometimes less, depending on the frequency. But overall, you typically average out to be fixed. Okay, some use more fuel, use less fuel, it's not going to make a huge difference to you. So that's fine. You can do this. So you have to do it if you're in the system, right? You're required to do it, but typically it doesn't cost you very much to do it. If you're power electronics, do you see some economic issues? And let's say if you're power electronic trying to do frequency response. Let's say if you're solar or your battery, and I tell you now you have to do frequency response, will you complain? Will there be something that you're not very happy about for this frequency response? Okay, so if you're solar, can you generate more power? If your frequency says generate more power, what happens there? Okay, so remember frequency, but let's say load goes up and you're solar there and then you measure frequency, it says, okay, generate more power. Right? So you may or may not be able to do that, right? You may not be able to get more power out of this. Compare that to a generator, a big generator, what happens is most times you can always shoving more fuel, will go up. It's not very efficient, but will do something. It's very hard to saturate a big synchronous generator. Giving more stuff will still output power. For something like solar, you're determined by nature. You're producing whatever you're producing. You can go down sometimes, right? You can go down in production. It's hard to go up in production. It's just yourself. Yeah. So right now is one, if you ask to do this, you want to get paid. You may not be able to always generate the peak capacity. So right now, what happens for a lot of solar and wind is you have this sort of 10% of 10% band as you go up to 90% of your max production. So you leave some wiggle room to do this kind of frequency response. Then you will want to get paid because you could have been generating more. Remember, for this kind of things, generating power is free to you. Okay, there's no fuel cost. It's free to you. You want to generate as much as possible. That's free to you. You can generate that. You want to get paid for that. That's the economics issue. That is fairly difficult right now. Nobody has a very clear idea. How do you compute this kind of economics? Okay, so that's something to keep in mind. As we talk about ancillary services, most of this will be still based on a very conventional system, where you're thinking about things that are synchronous generators with things like fuel cost driving the main operating cost of generator. If you go to the sort of things with zero marginal cost, that with sort of possibly high opportunity cost, things like wind and solar, then it's less clear how any of this will apply. These are some things that's fairly challenging to know what to do. I don't think anybody has a very good idea what to do there. So quite an active area of research for ancillary services and renewable. Okay. Any questions about that? Yeah.
Like regulations on the energy storage system, so they have to like provide some sort of frequency response, or is that just like a free for all right now?
Right. So there is a regulation. Actually, the regulation is FERC 842. What that is some order from FERC saying anything connected into the bulk grid has to do frequency regulation. So it doesn't single out a resource, but just says I don't care what it does. I don't care what the type of resource is. You have to do it. So I think it came out in 2018. I'm not sure when everybody have to implement that, but it is a rule now. You have to do frequency. So FERC has this tendency of just making rules and leaving to ISO to figure out, this how it will happen. So right now, a lot of people are trying to figure out how that will happen, right? But there's rules coming in as you have to do this. You're required to do it, and it's up to the ISO to figure out a way to pay you such that you want to do this, right? So that we don't know yet. We don't quite know yet. Okay, good. Any other questions? Okay, so let's now look at some of the mechanisms of, if you want to have ancillary service, what do you have to think about? This is a very sort of typical example of how shows you that you need to leave some resources in your network as backup, right? So this is showing two areas. So if you want, think of these two areas, one as Washington State, one as California. So we do have tie lines between the two areas. And what you can have is you schedule some flows on these lines. But what can happen, let's say California now experiences a generator outage. Okay, so if you experience a generator outage and then you still have these two lines, what can happen is if California has a generator outage, if you're utilizing both lines, then you need to send more power. So you're sending more power along these lines. So again, remember this is a connected system. So this happens for physically, automatically, right? So this generator go down. So there's net load increase here. We sense that we push more power this way. This happens sort of without anybody's control. Typically, this happens. Okay? So, but when you worry about it, you have too much flow on this line. So if you have too much flow on this line, the protection would trip. Okay? So you would almost never wait until something actually physically bad happens to the line. You have protection systems on the lines. It measures a very large current flow. The protection doesn't necessarily know what exactly is going on, but the way it's set is it measures a large current flow. We'll trip, we'll open this too. And then this can lead to sort of further imbalance. Right, so you can trip, right? So you can have an outage, then this leads to line overflow. Actually, both lines can trip now. Then you have even less generation coming here, then the frequency even gets worse than this kind of idea. Okay, so there's a very hierarchical view in the power system. It's basically each system should balance its own frequency. So each big enough system, your job is internally balance your frequency. You typically cannot count on you always getting power from somebody else to do your frequency balancing. This is because of this sort of protection issue, this cascading sort of possibility of cascade, as you have to think of each system. Okay, so when you're doing your resource allocation for California, often you cannot count on if I lose a generator, I'll get power from somewhere else. So you have to maintain your own balance. Okay, so this again, there's questions of, let's say California has a wildfire potential, they trip some lines. Can we not shift more power to California and help provide power from our state? Often you're limited by this issue. So you often limited not because a nominal case. We can often deal with a nominal case of how much power we have to send. But you always have to think about if something goes wrong, you want the entire system to still be okay. That's often the limiting factor for us. Okay, so again, the trick here is you have to recover fast enough. So what happens is minor sort of frequency deviations happens all the time. Okay, this happens every minute. What you need to do is you need to be okay. So often you want to measure how fast you can recover given a minor frequency deviation. Okay, so what you're afraid is a bunch of them sort of randomly adding up and force you into a bad situation. So small deviations are okay, but you always trying to recover back to the nominal load. So this is an example of how things look, actually. Okay, so this is showing you, think of this hours of a load that's ramping up, staying constant and ramping down again. So if you look at the actual load, there's a lot of small variations up and down. This is just random noise, basically based on individual behavior, random noise. Okay. So the way we do dispatch for this is you basically dispatch or you trade your energy, right? We solve this economic dispatch problem. These are a lot of variations. What do you pick? You pick the forecast. Okay, you trade energy on this forecast value. Okay, and these are, so this is 1 hour. So the forecast will say everything's constant within this hour. And so our energy traded is based on these values, based on the average forecast. And you handle the small variation by things like frequency regulation. Okay, so you trade on this, this is your target. Like for example, this thing will have random variations around your target. This will cause frequency change. So you automatically track this frequency change. Okay. So that's how a system under normal circumstances is operated. Any questions? Okay, so why do we trade things for an hour? Why not half an hour? Why not 5 minutes, right? Okay, it seems like, for example, this is pretty big deviation from forecast. Right? It seems like if I have narrower and narrower time periods, I can do a better job at meeting the low. I don't need this much frequency response within this 1 hour. So why do we have this hourly scheme? Why not do 30 minutes? Why not do 5 minutes? Why not do 1 minute at a time? But you can handle that as a constraint, right? You can say, in 5 minutes, they don't rest that much. Right? You can build that into the problem. Doesn't right? So even if you do this hourly, nuclear doesn't change within this whole period, right? So it's not like every generator will run within that hour. Right, but it seems that the finer the time period, the less variation, or you can take up more variation. It can be through more targeting schedule. So the answer, which is from a very practical reason, this is about as much as problem we can solve. This is this is a computational limitation. It's not a physical limitation. So if you basically what happens is the size of the optimization problem you have to solve scales with the number of generators and multiplied by the number of periods you consider. That's basically the size of your problem. Number of generators, not much you can do about that. Right. So if you go from, let's say, 1 hour to 15 minutes, you increase this by a factor of 4. This optimization problem is not linear in the size. They scale horribly in the size of the problem. Okay, so if you increase this to 15 minutes, you may not be able to solve this optimization within a day. Actually, even at hourly dispatch, most optimizations take you several hours to solve. Takes your computer several hours to solve this problem. If you go to 15 minutes, you can't finish solving this problem at the time. And so there's a computation limitation. None, right? So there's something to remember. It's really, a lot of this comes down to kind of solve the optimization problem, technically. So this is a limitation coming from there. And within an hour, so this is showing an example, lot can happen within an hour, right? So let's say here, what happens is you lose a generator. Okay? So this is a typical thing of a fault. This is generator loss. So you lose a fairly sizable generator. This whole thing comes down. This is the max you can generate. Then what do you see this imbalance as you observe this kind of behavior. Okay, so this are your imbalance. Normally your imbalance will be fairly close to zero mean. Then you have a huge drop. This will have dropped. Then a mechanism kicks on, this ancillary service comes online and try to recover this imbalance, try to drive this thing back up. Okay, so this is sort of random. Okay, so this is sort of random fluctuations. This is your outage. Okay, so we want to make sure that the system is okay after this kind of outage. Okay. And what you will see if you look at system frequency, you basically this showing power, but power is roughly proportional to frequency. So you'll see what happens is a very large frequency drop. Then everybody senses this frequency drop and then try to recover the system back up. So you do need, so that's why you cannot sort of commit all your power, right? You don't want this red line to be the maximum power you can generate. Because if this happens, the system still needs to stay online. And you still need some room to recover after you have a huge outage. Okay? So what happens here is this when this difference between load and energy traded, this is not handled in the market. Okay? So we don't handle this directly for a bidding market is not like I have a generator, now then you announce you have a generator, you do another round of bidding. Who wants to pick this up? This happens far too quickly for this type of bidding market to happen. So here, this thing, what happens is now you contract for service. Okay, you don't contract for the quantity of you provided. You say, I contract you for if this happens, you have to provide this service. And I pay you based on the service you may or may not provide, right? But pay you based on the capacity to provide this service. Okay, so the difference between energy traded and the energy produced, right? So here, so the difference between load and energy traded, this normally comes in the error in forecast. So we trade energy based on the forecast load. Forecast load is not the true load, so there'll be some error that need to be handled. There is also a difference between the energy you traded, you said you were going to produce versus the energy actually produced. There's what often happens is you will have sort of finite ramp rates. And so we trade on hour to hour, but between 2 hours, there's a step change, but take you some time to ramp. So that's one thing you will see. And then another thing you'll see is something like an outage, right? So outage will create a large imbalance. And balancing services, basically, these are the services you contract people to provide. Okay, they are done ahead of time. You're contracting now for capacity, not the actual amount of things you generate. Right? So when we run the energy market, you're being paid on the amount of energy you will generate. Balancing service, a lot of times you're contracting for the capacity to do something. Right? You may or may not need to do it, but there's a capacity. And the way this thing is organized is basically on time scale. Right? So this is organized based on sort of the different phenomena that you can have different time scale. Okay, so some things happen in second to second, some things happen minute to minute, some things maybe hour to hour, this kind of thing. And then you require sort of different services for each. Okay, so there's a lot of balancing services depending on exactly how fast you have to use the service. Okay, so, and the exact definition depends on the market. So different markets in the US take care of different things, but there's sort of the how exactly you call them matter. So we'll look at some example of this balancing services. The fastest services are something called the regulation service. Okay, so regulation service, what this does is they are responding to sort of this very small, very rapid shift. And their goal is just to keep the frequency close to nominal. Right? Okay, and what they need is you need to be able to adjust your output relatively quickly. This will be something like a gas turbine. So it'll be something like gas. They need to be connected to the grid. And you need to have this for automatic control. You need to be able to sense frequency and then control your output. So what does regulation service do? Regulation services basically track this little blue things. That's what regulation service provides. You have this blue uncertainties, you track, you cancel out, you balance out this blue things. This red curve, which is sort of the longer term average of these things, is done by something called a load following service. Okay, so load following service is you're not responding extremely quickly, but you're responding at a fairly quickly rate. Okay, so you don't have to respond within a second, but you have to respond, let's say, within a few minutes. And when you do it, you're trying to average out this sort of slightly longer changing things. Okay, so a good So a good time to have in mind is regulation service typically has a time constant or time of every 4 seconds. So what these things require is something that can change its output every 4 seconds. Has a large output, change the output every 4 seconds. So what technology can do this actually? What kind of generation, what kind of technology we have that can so rapidly change its output second to second? On a second level scale. Batteries, right? So this is actually for many markets, this is now cornered by batteries. Because what happens here is these are zero mean very fast fluctuations. So your battery, this is actually your favorite application. You don't need to generate anything net, you don't need net generation. All you need to do is respond. 4 seconds is extremely long for batteries. Battery can respond in sort of 4 milliseconds. Right, so this is very good for batteries. A time constant here for you to think of, this is something like 15 minutes or 10 minutes or so. The load following is you need to be able to change every 10 minutes. These are typically gas generators. You don't need to be that fast, but there's a longer up and down. Batteries are not great at this because this requires you to have a very large battery. You may have something that's for positive for an hour, negative for the next hour. Battery typically requires something that averages out a bit faster. Okay, so this is called a intra period. So 10 minutes within the hour, you're doing some services here. Okay, and if you're running a system, you're paying a bunch of people to do regulation, you're paying a bunch of people then to do load servicing, you're paying for all the entities to do this kind of work. Okay, so this gets into something called automatic generation control. And really what this is, so both of these services, load following service and regulation service, are called automatic generation control because it doesn't require the dispatcher to do something. As you still measure a frequency deviation, then you try to correct for this frequency deviation, right? There's not a market on this. You don't bid into this. And what this happens, this is fairly easy to compute. What you compute is something called area control error. Area control error says if your area, this ACE is basically the net imbalance. Okay, so area control error is a net imbalance within your area between load and supply, between supply and demand. And the way you calculate this is there are 2 things you sum up, basically, is you measure frequency, you measure your frequency. This thing gets subtracted from the nominal frequency. This goes in the box, and what this converts into power. So area control error is in terms of power. So you measure your frequency, this in terms of, let's say, hertz or radians per second. You multiply by constant, get into power. You add something to this, which is your schedule interchange. And so how much you're supposed to get from the other area. The output is the area control error. Okay, so what is the imbalance within your own area as shown up by the frequency? This plus how much you're supposed to get from the other people. This add them together, this is the control error. What is the net imbalance you see in your area? And by computing this error, you can figure out what you do, right? You figure out how should you change your generation to make this error 0. Okay, so ACE is something you track, and you want to make sure that this thing is driving this error to 0. So there's a very sophisticated control back behind this. We're not going to go into this control. It's quite tedious to draw everything out. But just think of what we're doing is every 4 seconds, we're computing this error. We're sending this error to all the generators in the grid. They respond to something, you keep doing this. And hopefully this error will go to 0. Hopefully you can minimize this error. So that's ACE. That's basically based on frequency. And then something that's also you call on is reserve services. These are things that handles large deficits. These are big generators. You have to call them to be turned on. They don't directly turn on because they measure frequency change. These are generators. The operator sends out the signal telling them you should turn on and respond to an error in the system. Okay, so we'll take a 5-minute break. Then we'll look at this reserve services. Okay, so there's an interesting bit of market behind reserve services here. This predictable really means that you know the range this up and down will go. Okay, that's predictable in the sense that you have a fairly good stochastic characterization of what these things are. Okay, so you don't know exactly the value, but you know the form of the regulation service you have to do, right? So you know, for example, you're going to go up and down between 1 megawatt every 2 seconds. You know this kind of thing. So that's what calls predictable. So if you're a storage participating in regulation, you have a good idea of how you should size your storage. You know how big you have to be, you know your energy rating, you know your power rating. Okay, so that's what predictable means. You're always doing something and you're just there. This is, again, if you recall the terminology, this is called preventive actions. Because we're putting to the system, it doesn't matter what happens, they're always active. Okay, they're just there to do something. They're always be in the system. Reserve services, this use is unpredictable because you may not have to use reserve services if an outage doesn't happen. Okay, so what this means is really if you're reserved, you're waiting for the system to have an outage. If the system doesn't have an outage, then regulation is good enough to pick up the need in the system. You never get used. Okay? So whether you get used or not, you don't know, right? So this is called corrective because you only get called if something big happens. And so here, if you contract for capacity, you just contract for this capacity. You know how much you need, you pay these people. Reserve service is a bit more intricate because if you're a generator, you're thinking, should I be a part of the reserve? Well, I have 2 choices. I can either be on reserve or I can actually generate power, right? So I'm on reserve. Depending on how you pay me, it may or may not be worth my while to be on reserve. If you have a payment scheme that only pays, if bad things happen, then I may not get a lot of money. I may lose, I have big opportunity cost. But you do need some things to be on reserve. So the market setup is a bit more challenging, where these things essentially happens as an added part of the market. You just take whatever power you need, add 5% to it, and get some people to do this kind of action, or just pay them based on this. This is harder. This you have to think about how if you're a generator, how do you balance between actually serving, right? So the benefit of being a reserve is you may get paid without the need to do anything. You may just sit there, you don't have to if nothing happens, then you still get paid. You have 0 operating costs, you get money, right? But then, so the question is how much do you pay these people to be on reserve? Right? Their benefit is they may get free money, but they may not get called. How do you pay them? So we won't get to this class, but on Friday, what we'll do is we'll do one long example that has reserve services. We'll look at how this whole thing gets clear with reserves. But right now, just remember, it's not trivial to compute the payment scheme for reserve services. Okay, do they get paid on what they actually do, or do they just get paid by being there? Then you run into the problem that they may not do anything. Right? So they're just making free money. Right? How do you ensure that things are fair? And to determine how much reserve you need, so you basically as a system, you have to compute. Again, regulation is again easier. you just add 5% to it. How much reserve you need, you have to think about what are the bad things that can happen in your system. These are not small variations. These are caused by events. So the way you calculate how much reserve you need is you have to think about different contingencies, right? What are the contingencies that could happen in the system? You need enough reserve for your system to survive this contingency. And the key word here is to read credible, okay? So if you cover this word and say no contingency should destabilize the system, again, it's not a tractable problem. There's way too many things that could happen in the system. It's very hard to even compute what reserve you need. So the reason you add the word credible is that you say, okay, I cannot look at every possible combination of contingencies, right? Then here is really anything that can happen, right? Anything that would happen, I need to consider. I can't consider them all. Okay, if you do optimization in power systems, there's many people who build their whole career computing contingencies. How do you think about more contingency in the system? But still, you still need some list. You cannot consider all of them. So what is credible contingencies? And this is where, this sentence basically is wrote by a lawyer, not an engineer. And this is you have to argue. Okay, so, so for PG&E that got sued because they have a power outage, most time you argue it's credible. Could you reasonably have known that contingency could have destabilized the system? Right? Should you have known that? Should you have planned for that? What should they have done? Okay, right. So a lot of people, spend their career on this, and the goal for engineers is try to expand this one. You want to look at a bigger set of contingencies. That's where a lot of computational approach research is done to expand that. Okay. But for us, is to look at what are different things that can happen that can cause destabilization. Right? How will these things happen? So there are typically three modes that can cause things to become destabilized. One is thermal overload. Okay, so this means your line is too hot. So you have a line, you're running too much current over this line, the line is too hot, the line cuts out. That's a contingency. That's a line outage contingency we care about. There's something called transient stability. This is the harder contingency to understand. This is basically the dynamic behavior of your grid. If you have a disturbance, what happens after this disturbance? This is similar to voltage instability. Okay. So the difference here is thermal overload is your line heating up. This is in some sense just the line heats up and then the line has outage. You have to think about the rest of the system. This is not really a dynamic behavior. These are dynamic behaviors in the system. So this is way too out of scope of this class. It takes a lot to get into this. So we're not going to think about stability. We're going to look at an example of thermal overload and see some of the consequences of the fact that you may have thermal overload in the system. Okay? Right, and to do this, again, you have two kinds of actions. You have here one called preventive, right? So low cost or high cost. So low cost are things like you can do without impacting customers. Really, these are the things that customers will not notice. These are the things that the customer will notice. Okay, so these are things like your adjust transformer taps. Okay, so something that happens again all the time that we don't notice it. You can have just phase shifters. Okay, so phase shifter is something that in the system can shift the phase of AC voltage. So these are examples where you don't notice. We do them all the time. You don't see them. And then high cost, this is load shedding. You may have to share load. And this again will impact the market. Okay, so the high cost ones typically impact the market. So to deal with the cost and the right. So if you promise a generator, they can generate, they actually cannot because contingency, you have to sort that out based on what happens in the market. Okay, so one example for thermal capacity and the way it impacts is, let's say you have A and B and this have a load. Okay, and let's say you have two lines. Each line of them is 200 megawatt. So you have 200 megawatt on this line, 200 megawatt on this line. Okay. Then what thermal capacity tells you is actually you can only use one of the lines. Because what is the possible contingency in this case? As one of the lines may fail, right? So you can compute. So this illustrate the difference between critical contingency and all possible contingency. So what is the set of possible contingencies here? Well, the set of possible contingencies is this generator fails, that generator fails, both of the lines fail, right? If you consider all of them, then this problem is not solvable, right? So all bad things can happen, and every generator can fail, then your load, there's nothing can supply the load. Okay, so typically what's considered here, the critical contingency is not both lines fail, but one of the lines will fail. We consider that to be critical. That's something that can reasonably happen. Then what the outcome of that contingency is, you can actually only use one of the lines. You cannot use both lines. You cannot actually use both lines for starting power. So one of the lines there's no power flow on this line. The other line will have the full power flow because you're protecting against the fact that there may be a line outage. Or more physically correct, as if both lines have a limit of 200 megawatt, we can do it. You send 100 megawatt along both sides. If one fails, the other one carries all the power goes through. Right. So that's the idea of this thermal capacity limit. So you keep this 200 megawatt in reserve. Okay. So if you build a line and you ask the question is, okay, how much more money can you get by building this line? You got to think about this kind of reserve cases. It's not that you build one more line here, you can flow through 200 megawatt more. Right? So if you build another line that has a capability of say flowing 200 megawatt, again, you have to think about this contingency. You have to always think about this kind of contingency, what has happened. Right? So normally if you have a situation, let's say if there's only one line connecting these two areas, normally you don't use that line at all. Actually, normally you don't flow power along that line because of contingency, right? So if you only have one line connecting two areas, it may be possible for that line to fail. Then if it's possible for that line to fail, you cannot use that line, actually. Okay, so normally when you look at this kind of things, you need multiple lines connecting every area, all the areas. So it's not as simple as just having one line there. Okay, so reliability is an important thing. Okay, so this is obviously, this is not great. You're building one line just for backup. So way is to say, what happens if you have emergency thermal capacity? So now it's right. So we used to do this. We used to just say you have a thermal capacity, you keep one line as reserve. Something may happen. The thing is, so now the systems are all operating much closer to capacity. So we want to squeeze more efficiency out of this. So now systems are employing something called emergency thermal capacity. So let's say your line is overloaded. Physically, what happens if your line overheats? Again, what are you afraid of if your line overheats? Right, you're afraid the line will sag. The line doesn't melt. You can't actually melt the line, right? You're afraid the line will get longer and longer, will sag. So what controls how far the line sags? Right, thermal expansion. It takes some time for thermal expansion to happen. Okay, so what says is the line, once it overheats, goes from 200 to 201. It's not going to immediately sag and hit a tree, right? It takes some time for thermal expansion to happen. There are people, again, who build their companies doing this kind of heat flow analysis on lines. So now it's pretty popular to look at emergency thermal capacity. And what you say is each line has a 10% emergency rating. For 20 minutes. Okay, so what this says is you can actually operate above this 200 megawatt range. 10% more for 20 minutes. That's the amount you're allowed to operate above. Because thermally, again, it's not going to heat up immediately if you exceed this number. So then we really are looking at is if you have this generator, how fast can you run? Right? So this will be something like a non-spinning reserve. Because here we're assuming A is cheaper than B, so A is trying to supply the load. Now, if a contingency happens, this generator has to ramp. Okay, so what this does is you basically give some time for this generator to ramp up to supply the load. Okay, so this is non-spinning reserve. It needs some, let's say 20 minutes to ramp. So if generator B can ramp up by X megawatt in 20 minutes, let's say by 20 megawatt by 20 minutes, then A can sell to 20 megawatt to B, right? So if you have a non-spinning reserve that can run in 20 minutes, you can transform more power. And this one, A can make more money, two, the price actually of this will go down. Okay, so increase the efficiency. But then you have to pay this generator. Even if this is an extremely expensive generator that will never get used in normal circumstances, because this generator is allowing you to transform power from A to B. Okay, so that's the value of reserve. It basically allow you to enlarge your sort of feasible region of how A can sell to B. So this generator, just by being in the market and being there, can increase the efficiency of the market. Okay, so you have to pay. So the payment scheme is you have to figure out a way to pay this guy, right? Just being there. So you have to think of how does the price change. You have to compute the price. So this will be at a different marginal price than say if you're just selling 200 megawatt. So a different marginal price. We'll compute how much of that goes to A, how much of that goes to B, and we'll do all this kind of calculation. Okay, so again, we'll see this full example next week. But the idea is illustrating it's useful to have reserves, and you have to pay this reserve some money. Okay, even though you may never use this reserve. You hope to never use this reserve. Any questions about this? So again, if you need something to think about, what is A, what is B, think of A as Washington and BC Hydro. B is California. This is actually a really good model of these two systems. California has a very big demand. Hydro is really cheap. So we try to send power down to California. We typically are limited by transmission. Not exactly by thermal limit, but by the transmission limit. And there's a whole bunch of ideas trying to increase this transmission limit. Question? Okay, all right. So this is the thermal limit. Again, we're not going to really consider transient and voltage stabilities or beyond the scope of this class. They are much more transient and voltage stability are more technically in some sense more interesting, but it requires a lot of details about power system modeling that we're not going to do. Okay, so we're going to look at another one that's interesting. I'll say a few words about this. It's called Black Start Restoration Capability Service. What this means is, imagine you have a system that gets completely wiped out. Okay, the whole entire system got destroyed or stop supplying power. Okay. Black start means a generator that can start when there's no other source of electricity. An example of this will be something like Hurricane Sandy in 2011. Hurricane Sandy wiped out a lot of generation in New Jersey and New York. How can I do black start? For example, this will be 2003 blackout. New York again was entirely blackout. Can a generator start after the whole system goes down? Okay. So why is this important? Shouldn't all generator be able to start? Your synchronous generator. Why does your generator need some power to start? Right, so one is you have to run, right, there's some equipment you have to run to get a generator started. The best example of that will be actually be hydro. So you cannot black start a hydro system. The reason is you need some power to open the valve on the hydro system. You need power to adjust that. Not, you need electric power for that. A hydro system wouldn't start on its own. Again, same thing as for nuclear, you need to cool the nuclear power plant. Can cool it on its own. Okay, so there's not many plants actually can do black start. So this is an important service capability that you contract out to some generators. So there are some generators who's designated to be black start generators, and then they will start up, and then they will create a 60 Hertz synchronous signal, and then we'll bring the other generators back in sequence. Okay. So there's a very so there's actually a very particular server sequence for all the systems. So you look at the menu, every system will say, if the entire system experiences a blackout, there's a sequence of which generator you start. Actually, it takes a while for the entire system to come back online as you start the sequence. Okay? So these are typically sort of large gas plants that can start spinning, that can create frequency and help other things. Okay? So the question is, how do you pay this kind of thing? What value do you put on black start? And you have idea, like let's say you're a generator, you can do black start. Of course, you want to get paid, right? You're providing a unique service. How much do you get paid? How much do you get paid? Right. So this is often the question that comes up in power system economics. As how valuable is this service? Well, this service in some sense infinite value. Without a black start generator, the whole system doesn't work. Right. So it's our infinite value. But you use this thing once every 20 years. Right. So the Pacific Northwest system has not experienced an entire blackout within the last 40, 50 years. We pretty much never had a huge blackout. Okay, so you're balancing something that's with very extremely high value with something that's extremely rare. You multiply these two big numbers together, you try to come up with a number. Not clear what this number is. There are sort of trials. So there used to be basically you just assign a generator that you're doing black start. I'm going to pay you some money. You're contractually obligated to do this. Now there are markets that start trying to, people are trying to push markets for black start restoration. This is again both because coal and gas sometimes are good black start generators, and this is a sort of resource that's needed. So people are starting this kind of market, but then there's a very new market. So contracting market for black start is something new. It's something that will happen more and more often. And more often in power system, we'll see extremely, we'll be trading off against two extreme values. How do you calculate that? It's become more and more relevant. Things like, if there's a possibility of wildfire de-energizing a line, you're multiplying, you're trading off two horrible consequences. You have to assign a value to that. Here again, you're assigning a value to this kind of services. Again, so that's something to think about, which we don't have a very good market for this yet. We don't know how to value this kind of market. That's just something to know. The questions about ancillary services, or these are all the types of services you might need to run a system. And you're mandated of what kind of service you have to have. So again, FERC will mandate you have to have this kind of services. Then each system operator designs different rules and markets to obtain this kind of services. And so normally the role of FERC is to say what you have to have, then up to the system operator to figure out how they get it. And each system operates very differently. Like we'll operate very different than California operates. Okay? So there's different roles in it. So next we're gonna start really looking at how much do you pay, right? So if you're a system operator, one is how much do you want for each of these services? How many black startup generator do you want? How much spinning reserve do you want? How much frequency regulation do you want? How do you get them? Do you just assign it to different generators? Or do you have a market? And third is who pays for these? Because if you look at the market reform that's happening in the US, this is where the big reform is happening. Trading energy is typically considered to be fairly simple. We have a locational marginal price, you price there, you trade energy that way. Ancillary services is more questions being asked. So there'll be a lot of reform that's trying to happen here. So again, you have to think about how much reserve services you want. Well, a system operator is buying this reserves, right? So you buy on behalf of the system. So we are paying for these services. You're paying for availability, you're paying for capacity. Okay? So you have to think about capacity. And you're balancing basically one is you don't have enough, you can't ensure the security of the system. You have too much, we're paying too much. So we are the one, the users, the load pays for this. The generator don't pay for it. The generator provides this kind of services. The load pays for this. So if you buy too much, the cost eventually gets paid to the users, then which is people are not happy with this. Okay? So the system operator faces this problem. And we'll sort of this last thing we'll cover today is what the system operator is trading off is the value of services versus the cost. Okay? So the idea is, the more the better, really, the more the security, but the more the costly. And this gets to be a very complicated optimization problem. So if you write this out, really this is a complicated probabilistic problem. Okay, so you're optimizing cost against some probability of failures. How you assign the probability is hard. How you solve this problem is hard. How you come up with credible contingencies is all very challenging for this. But this is what operators are thinking about. Okay, so a lot of research that goes on, again, they're trying to solve this problem, formula and solve this problem. So the outcome of this problem is we'll have financial incentives. So basically a pricing that comes out of this optimization problem. Okay. So today we'll stop here. Next class, we'll look at a extremely simplified version of this, which is we'll remove all the probability, we'll remove all the trade-off, which is answered with one scenario of a taste of this optimization problem, which will take us like an hour to go through a very simple problem to give you a taste of how to do this thing. Okay, so we'll stop here today. Again, your last homework will be based on this type of questions. We'll ask some of the game theory questions, we'll look at reserves, that'll be your last homework. And so you look at the union of your homework questions, that'll be your final exam. Right, so final exam will be a subset of questions. Each of them will be similar to the homework question. Okay, all right, thanks.